to start today with the young session of our seminar. And the first talk of today is Jorge Zavaleta from Instituto de Matemáticas of UNAM. And he's going to present some radial basis function methods with hybrid kernels applied to control problems. So thank you very much, Jorge, for us accepting to give the talk.
Thank you very much. I want to thank George for you to present this job. This is of my PhD research in advance of Pedro González Casanova from Mathematics Institute from Universidad Nacional Autónoma de México. This is going to be a different talk from previous talks that we have in the seminar, because I am more focused on numerics, so I'm not very related to control problems. So it's going to be more focused on numerics in this way. So I'm going to give a brief introduction. I'm also going to define RBFs and hybrid kernels, and I'm going to show a method to apply to solve control problems. And at the end, I'm going to give some conclusions and future work. So radial basis functions are highly effective mesh-free methods for the solution of PDE problems. These methods can be divided into global and local techniques and have been applied to several fields, including convection diffusion, Navier-Stokes, atmospheric global electric circuit, shallow water simulation, reaction diffusion on surfaces, time domain elastic wave propagation into the isotropic media, heat flow, among others. Within the context of the RBF theory, few works address the solution to these problems of optimal control. So, for example, to solve distribute optimal controls, the first Poisson did the first application of global collocation methods to solve Poisson constraint optimization problems. We extend this work to convection diffusion, and also we are the first to implement local RBF methods with extended precision in order to apply these methods to larger problems. One and Xu, they apply global collocation methods to boundary optimal control, but they use elliptic PDEs as constraints. On the other hand, we have controllability. So the only work that I am aware that use radial basis function methods to solve numerically controllability problems is the work done by Breton, González Casanova, and Montoya. They use global collocation and local methods to solve the null controllability of Stokes equations. So there are very, very few works related to this topic. Why to use RBFs? RBFs methods have the following advantages and limitations. They are mesh-free methods. It means that we work with scattered data in RD. So we are capable to handle complex boundaries because only we manage scattered data, and also reduce numerical complexity due to avoid the generation of a mesh that is needed for other methods. So also we are going to have exponential convergency for some kernels. It means that we have high order approximations. And other advantages of this method is that they can be extended easily to higher dimensions. So this is because the gram matrix related to these methods have the same structure for all RD. And it means that they are easy to program. But the main drawback of these methods is that the exponential convergency implies exponential increase of the condition number of the gram matrices. So to address this problem, we are exploring different ways as, for example, extended precision. This is the one that we use in the article, and we report there. And also we are looking for another ways to address this problem. For example, polyharmonic splines plus polynomials. And presently we are looking into hybrid kernels. So In this talk, we are going to give some insight into RBF methods with hybrid kernels, and we are going to give some examples of their application to the numerical solution of control problems, specifically distribute optimal control problems that I was working in. And also, I'm going to give some, not very detailed, but I'm going to give some insight of null controllability of Stokes equation. To give the idea of RBFs, I need to start at the beginning of these methods. So I'm going to consider a scattered set of data, which is pairwise distinct, and an RBF interpolant is defined as the composition of a function phi with the Euclidean norm, and centered at the set X. And also it's common that they have a polynomial. In order to obtain the coefficients of this linear combination, I need to impose the interpolation conditions. It means that it should be exact at data, and also the moment conditions if we have a polynomial to obtain an algebraic system where A is the Gram matrix. This Gram matrix is non-singular for some choices of the function phi. These are examples of choices of these functions. We have different kinds of functions. For example, we have piecewise smooth functions, which mean, for example, one of these kind of functions are the polyharmonic splines, where are only the power of the Euclidean norm for odd or even. It's instinct. And also we have infinitely differentiable functions, for example, Gaussian multiquadric and inverse multiquadric. These infinitely differential radial functions have an additional parameter that is named the shape parameter. And up to now is one of the challenges in the theory of radial basis function, how to obtain a good shape parameter. Nowadays, for example, it is a user-defined parameter, but all depends on the data that we are using. So to give an idea of how this shape parameter affects the radial basis function, here is some example. For values near to 0, we are going to have flatter functions, and for greater, higher or larger values of the shape parameter, we are going to have sharper functions. So in terms of convergency, we are going to look at this because they have better results in accuracy, but also it affects the stability of the methods. So here is an example of how this subject is active field of research in the radial basis function theory. So here's an example, up to since the very early stage of the radial basis functions, there are some strategies to find an optimal shape parameter, but now, 2018, 2020, there is also several papers related to finding an optimal shape parameter. This is an active and open problem that I think is going to be active for a long time. Well, this is about the radial basis functions. I'm going to talk about hybrid kernels, a special radial basis function that we are going to use and has some special properties. These kernels were introduced by Mishra, which are the combination of Gaussian kernels with powers, with radial powers, and this means all PHAs. So we are going to have a extra parameter gamma, which controls the portion of polyharmonic participates in the combination. So, for example, we want that this parameter gamma should be very, very small, but sometimes it affects the lection is not really clear up to now. So the Gaussian component indeed is said to contribute to attain exponential convergency, and the polyharmonic part control the stability. It has to be with the condition number of the scheme. So we want this gamma parameter should be small enough to have the good properties of the Gaussian kernels, but we don't want to be zero because it controls the stability of the methods. So it's easy to show, or relatively easy to show, that that the hybrid kernels also are positive definite. To do this, we characterize the radial basis function through its Fourier transform. So so we use this theorem that is classical in radial basis function theory, that is an extension of Bochner theorem, that characterize positive definite functions through its Fourier transform. So we can see that this is the Fourier transform of the hybrid kernels, and also it's easy to show that it's not negative and not vanishing, and then is also positive definite. We want that the function is positive definite to guarantee that the gram matrices involved in these methods is also positive definite and then non-singular. No? So in this way, we are able to prove that invertibility of the matrix that is in the interpolation problem. So we have an extra problem, how to choose these parameters in such a way that also we have a balance between accuracy and condition. Only the election of shape parameter is an open problem, and we are adding an extra parameter gamma in this combination. So it's also more difficult than the previous problem. So to simplify this selection, we were trying to do some we were trying to prove some properties that appear in polyharmonics invariance under uniform scalings. So we apply this idea so that we can give us a guess how to choose these parameters. So so we consider a scale domain where h is a scale factor, and also we define an interpolant in this set and in this domain. It's almost the same. The nodes that I was considering in the not scale domain, it's only, and they are related. So we define this interpolant. Here I'm going to avoid polynomials to simplify the notation, but it's also valid in this stage. So also I'm going to set one of the parameters as equal to 1, gamma parameter, and let free the other one. So indeed I'm going to look out of this interpolant. What we want to do is to characterize the interpolant sigma, which is I am interested on, by means of this other interpolant. So it is relatively easy to show that the interpolant are related. It means they are defined the same interpolant. If we consider these values for h, also for the other parameter epsilon hat, and also the coefficients of the linear combination. But one property that I really like is that also under uniform scalings, we have that the condition number preserves. This is one property that I am looking for these methods, and also give me some guess of how could I choose these parameters in the election of the hybrid kernels. So this is one of the results that we are working on. But for example, I was doing some numerical tests to prove or to give more how to say to give some knowledge on how to choose the other parameters. So I've been doing some numerical tests. I've been considering the same interpolant, and I found that a good value to the shape parameter is given in this way, as a square root of the power of the polyharmonic of the number of the nodes that are in the set. Here is a constant, but is function of the number of the number considered in the set of scatter nodes, divided by the radii of the smallest disk enclosing X. So in this way, there are constants C1 and C2, such that for all parameters gamma that I could choose, we have that the condition number is going to be bounded. And so this is going to give us a good approximation. For example, no? Oh, we want to extend this result to, well, first I need to prove it. I haven't been able to prove it up to now, but it give me some way to choose the parameters to have good results, numerical results, but I need to prove it theoretically, and also to extend it to higher dimensions. But also we were working on results in general. For example, we can see that the condition number of the Gram matrices related to use hybrid kernels are bounded. This bound is, we think, is not tight enough, but it gives us some guess of how to choose the parameter and how they affect the. Give us some guess about how we can bound the condition number, for instance. But we are also working in a lot of results. I'm going to give them later. Okay, well, and how could you use these methods to solve control problems? Well, I'm going to give some insights on optimal control problems, and I'm going to mention something about null controllability, but we are working on this in this way. So we're interested in finding the solution to the following distributed optimal control problem. Here we want to minimize this functional. Here y is the state variable, u is the control function, beta is a penalty constant, and is it subject to fulfill this boundary volume problem. Here E is a PDE stationary linear operator up to now, and B could be any boundary operator, Dirichlet, Robin, or Neumann. To solve this problem, we are using an approach called optimize then discretize, which means we are optimizing the continuum and discretize the optimal solution. So to do this, we are using the Lagrangian formulation to using Frechet derivative to obtain the Euler-Lagrange equations. Here we have the adjoint equation and the state equation. Then here we are going to apply the radial basis function methods to solve this problem and obtain the optimal and the optimal state and the optimal control. The first Poisson was the first to use global collocation to solve this kind of problems, to a Poisson constraint optimization problem. But we work, as I said, in convection diffusion, but applying local radial basis function to extend their use to a larger problem, because this was the main criticism to the method that was given by Poisson, but it can be solved by using local radial basis function methods. Here we are using classical methods to solve PDEs by radial basis function. Mainly we are using global asymmetrical location, but also we propose two local methods, local asymmetric method with differential quadrature and local asymmetric applied twice. These methods are very well explained in the articles for the person who wants to look at more for this. But now we are using radial basis function finite difference. These finite difference radial basis functions are an extension of the idea of finite difference in a scatter setting. We want to discretize the operator by means of the functional values of the function, but we don't know these two quantities. So to estimate the weights that are involved in this linear combination, we use radial basis functions to estimate the weight, and then uses this discretization of the operator to generate an sparse matrix to solve in some nodes, in specific nodes. Well, one of the problems we're going to show here is the Poisson problem control. Here we have Dirichlet's boundary conditions, but this is going to give us some insight because we have an exact solution. Here are some of the results. We are going to have that mainly we are going to have that global methods are more accurate than local methods, but here we can show that global methods and local methods have the same accuracy and also have the same condition number. In this table, we are choosing the shape parameter with my estimate of the shape parameter. So it is variable for all the problems. And also, as we need to to calculate the every weight in the discretization at every point, we are using a different shape parameter for all these discretization of the operator. So it is variable for all the disks that estimates the weights on the local methods. But also we are going to have that, for example, using polyharmonics plus polynomials, we are having that attain very high accuracy. But this is mainly for the polynomial approximation. Also, we are going to have that for more smooth functions, polynomials is not going to be good enough. And the Gaussian part of the hybrid kernels is going to have a better accuracy than these methods. So we also can use polynomials with hybrid kernels to attain the same accuracy as polyharmonic splines. So we have two ways to bound the condition number and also have high accuracy in these methods. Well, the other problem that I did not work directly, but I also know some of the details, and this was work of another PhD student with Professor González Casanova and Dr. Montoya, was the solution of the null controllability problem. We are looking at initial state, we find a control. We are looking for scalar controls that the solution at time t, capital T, we are going to have that this solution is equal to zero. In this problem, they proceed as I did with the optimal control problem. They are looking to minimize this functional, and to do so, they use the Lagrangian formulation. So incorporates the constraints to the functional and obtain this functional, then takes the Fréchet derivative to obtain the adjoint system. To obtain the solution of this problem, which is dependent of time, they use conjugate gradient method, and LHC, this is local Hermite interpolation with hybrid kernels of free divergency. I'm going to explain a little bit of this. To solve the Stokes equations and the joint system to minimize the functional G. So here they are using some of the results that were introduced by Wanlan. So this discretization scheme uses spaces of approximation that are divergence free. What does it mean? They can produce exponential order approximations, the high order accuracy approximation. Also, they avoid saddle point problems for speed and pressure because they are using the space that are considering divergence free, and they are not to fulfill the LBB or IFCE conditions that appear in methods like finite element. And also use a discretization space for velocity and pressure simultaneously. So they don't need to decouple the system. So they are solving a coupled system instead. Also, for example, for these, they were introduced for the stationary setting of the Stokes equation. They are using collocation-free methods, but also the local versions of divergence-free matrix value kernels. Here, where phi is a kernel like I defined before. Here are some of the results. I'm not going to explain much, but we can see how is the behavior of the norm of the state here, and how it tends to zero as the time goes to the time t. I don't know which is the time t capital. Here is for LHE Rbf using Navier sleep. I put the Dirichlet setting, but also they prove it by using Navier sleep boundary conditions. And this is the behavior of the same problem using finite element methods. And as we can see, we have almost the same behavior for all the solutions. Well, the application of RBS methods to the solution of the test control problems has shown good results and gives the possibility to extend them to other control problems. No LBB or IFCE condition is necessary. Exponential convergence can be obtained for smooth solutions. Navier-Sleep's boundary conditions can be easily incorporated to complex boundaries. And also during the study of the numerical solution of the control problems, we gave some theoretical and practical insight of how we apply these methods to these problems. And work in progress now is to solve the local controllability of the Navier-Stokes equation by these methods. Well, thank you for your attention.
Thank you very much. Other questions or comments?
Le puse
Lucero?
Oh, yes, please.
Okay, I just want to ask you something, Jorge. You mentioned at the very end that you were working on Navier-Stokes equation. Yep. So please let me know which kind of problem are you trying to solve, and which is the advantage of using radial basis method against finite element method? Is there something you get from using this?
Okay, method? So as I said, we are looking, one of the problems we are looking to solve with these methods is local exact contrariability. This is because the only paper that I know I have referenced is the paper of Professor Fernandez Cara, who solved by finite element this problem, and is a way to, this is a result that we can compare. But also we are looking to solve the problem of small time controllability, global controllability, that is being studied by Coron and I forget the name of the other.
Marbach.
Marbach, yeah. Marbat and Coron are studying the small time global controllability, and we are also interested in these problems. And the advantage here is that, as I said, there is no need to fulfill the LBB or IFCE condition because we are using divergency-free space of approximation. So this is one of the advantages against finite element methods.
Okay, so Victor Hernandez Santamaria wants to ask something. He says that you said you are following the spirit of optimize, then discretize. Is it feasible to do the other way around?
Yeah, this is possible, but in the first paper that was related by Poisson, he studied the bot approach, but at the end he gets that the very good results are with the optimize then discretize.
Okay. So if there is not other question, we pass to the other.
I would like to make a question.
Yes.
Yes, you have mentioned twice, at least, that the advantage of using free divergence approximation of the to the problem in the case of the Stokes and the Navier-Stokes equation is that you don't have to use an IFCE. You don't have to verify an IFCE condition, and it is simpler. Okay, I agree. How can you get an approximation of the pressure in these cases? How can you get the pressure there?
How can you get the pressure? Okay. In this manner,
yes,
we are using this to approximate the vector field. But for the pressure, we use a scalar Rbf. So they are coupled. I don't have I didn't put it here, but this is the idea, to couple, to give a divergency-free matrix value kernels by coupling this to approximate the vector field. And for the pressure, we are using, or they are using the scalar radial basis function to approximate the pressure.
So you get the pressure after the computation of the velocity field.
At the same time.
Is it all right? At the same time?
At the same time. It is not put here, but it can be, how do you say? Could I how could I say it? Excuse me, but a little bit nervous. You can couple the bot in a same divergency matrix kernel. Could I respond in Spanish?
Yes.
Yeah.
Yes, of course.
Enrique understands, not the rest.
I know because they understand.
With Andalus accent, please.
Sorry, but I not. Lo que pasa es que hay que generar una matriz, un kernel matricial de divergencia libre al meter, por ejemplo, este aproxima el campo de velocidades. Y aparte se puede meter para aproximar la presión una función de base radial escalar y la podemos acoplar en el mismo kernel matricial, de tal manera que pues cumpla las condiciones de divergencia libre, es decir, esta parte de aquí, para para la velocidad, y para la presión simplemente pues la aproximo como una función escalar. No sé si...
Pero may I make an observation?
Yeah.
Yes.
There is a work made by Fuselier, and he used Hodge decomposition. So he first approximates the velocity and then the pressure in an iterative procedure. That's one way of doing it, and it's very fast. Now, right here, what we're doing is, as Jorge says, we couple both the velocity field and the pressure in the same algebraic system. And that is possible. We solve it by conjugate gradient. So there are the two possibilities. You can decouple by using Hodge's composition, or you can use it in the same linear algebraic system. I don't know if that answer.
Okay, okay. Thank you.
Okay, thank you very much. I think we have to pass to the other talk. So thank you again, Jorge.
Thank you.
So now is Lucas Machado. So can you share your screen, please?
You can see?
Yes, perfect. Thank you very much, Lucas. So Lucas is going to talk about some control results for Stokes equations with memory. So please, you can start.
Good afternoon, everyone. I would like to thank you for the invitation. I will present some control results for Stokes equations with memory. And the main result is lack of the null controllability for the linear Stokes equations with memory. And that was obtained in collaboration with Henrique Fernandes Cara and Diego. This is the presentation plan. First, a brief introduction and some previous results. Next, I will present the main results of the non-null controllability of the linear Stokes equations with memory. And finally, some additional results and comments. Okay. Introductions. Well, we will work with these systems, okay, where U represents the velocity of the fluid and P is the pressure. And we will call these equations of Stokes with memory because if B is equal to 0, we have the well-known Stokes equations. And if B is different to 0, we have this no local time term in blue here, called memory term. And then we will consider B different to 0. And we have this term, okay? This kind of equations can model viscoelastic fluids, for example, blood, saline, paint, running, polymers, for example. Well, our goal is to analyze the controllability of the Stokes equations with memory, but first same definitions here. Control systems are those whose behavior can be influenced by the actions of the additional variable is the control, okay? Where U, the system is like this, where U is the state and V is the control. The variable V is a free variable and chosen in order to achieve the objective. Some time of controllability are exact, null, approximate, for example. And for the exact controllability, we start from n initial data, U0, and using control V, we can drive the solution U at time t to n desired final state ut, okay? And null controllability is a particular case where the final state is the null, okay? And for approximate finite dimensional controllability, we start from n initial data, u0, and we can drive the solution u to a neighborhood of the final state ut, okay? And on m, it has an equality. Here, m is an finite dimensional space, and in it, okay? Here, we have a nonlinear system for a viscoelastic fluid of the odroid kind, okay? And here, u and tau is the state, and v here is the control. Well, this model is non-Newtonian homogeneous fluid with memory, and the system is more difficult to solve than Navier-Stokes equation, except for particular cases. It open the existence of the global weak solution. Then it is natural to analyze a linear version of this equation. So we have the linearized viscoelastic difference fluids, okay, here, these equations, and you can solve this equation, and you replace resolving tau and replace here in this equation, okay. Then we get this integral differential equations S, that is Stokes equations with memory, okay. Well, for these equations, as Ana Dobova and Henrique Fernandes Cara proven for a result of approximate finite dimensional controllability. Is this, okay? Then for all little omega, the system S, Stokes with memory, is approximated finite dimensional at any time, positive time t, okay? For this, and unique continuation property has been proven, which is equivalent to approximate controllability. And this theorem is for distributed controls, but the same results for boundary controls is valid. When nu is equal to 0 in S, we have the linear Maxwell fluid, okay? And in this case, Boldrini, Dobova, Fernandes Cara, and Manolo Burgos proved for suitable omega and large time that the linear Maxwell fluid is exact controllable, okay? And when B is equal to 0, we have the well-known Stokes systems that is null controllable. Well, on the other hand, considering Reed instead of Stokes, we obtain the Reed equation with memory. Here, we don't have pressure, and not that here the controls is acting on the boundary, okay? Then Guerrero and Manuvilov proved that the Reed equations with memory is not null controllable, and the same results for distributed controls is true too, okay? Well, then we know that the Stokes equations with memory is approximate controllable, and that we don't have null controllability for similar equations in the case with the equation with memory. So a question is what can you say about null controllability for Stokes equations with memory? No? Is there a controversy that U in final time is equal to 0? Well, the answer is no. We prove that there are initial data that cannot be derived to 0, okay? This result is proved in 2 and 3-dimensional cases, and here we consider the similar boundary problem, okay, where the control V acts on the whole boundary, okay. Well, for the systems, we prove that there are initial data U0, so that the solution is not null at final timing for all control V, okay. Here, we present the sketch of the proof, which is inspired by Guerrero and Emanuelov, okay. And the first point is that is not restrictive to consider omega as a ball with center 0 and radius r, okay. Because you can use a argument of extension domain, okay. Another point is that the result of null controllability is equivalent to the following observability inequality for all phi t, where phi t is solution to the adjoint problem and phi t is the data, okay. Then we will demonstrate that the observability inequality is not true for every phi t, okay. Here we will consider the 3-dimensional case, okay, 3-dimensional case, and the fact that we are in the ball allows the obtain an explicit sequence of the age functions pk and the age values lambda k of the operators Stokes operator, okay. This pk is this, and qk, the pressure, is null, okay, for all k, and lambda k is basically k squared, okay. We will also obtain the estimate for the normal of pk and its normal derivative on the boundary. It is necessary to compute some things. Well, we taken phi t as a linear combination of the age functions pk, okay, and the associated solutions is this has this expression, and with this the pressure is null, okay. Bem, alpha k has this configuration here, where mu is known, and C1 and C2 is now C1 and C2 is equivalent to now BK, okay. Well, then we will choose BK this way, okay, and in a sequence of 8 consecutive numbers, depending on the parameter m. Okay, this. Then, our goal is to construct for m large a sequence of solutions Pm such that we have these estimates in star. These independent of m, so not that the exponents of these terms. Here 6 and here 10. Okay. Well, do the ordering of these exponents and the fact of the pressure is 0, think m large enough, we have that the observability inequality is true. Okay, because here the pressure is 0. Here you estimate for M10, and here estimate for M6. For M large enough, we have the contradiction. Well, and therefore we don't have null controllability. Okay. Now let's get the estimates. This estimates the key here and stuff. Okay. Well, first, the estimates from above. To simplify the computations, we introduce the weighting, exponential weighting here, okay? And do the alpha k, we estimate in 2 terms, A1 and A2. In this lemma is the estimate obtained for the term 1A. We intervene by parts these expressions, okay, and the coefficient is known, but this term don't have a good estimate, okay. Then we impose in these conditions. Then we don't have this with these conditions. But this is equivalent to have a homogeneous system with 5 linear equations and 8 known BK. Okay. Well, in this lemma is the estimate obtained for the term A2. Here we spend this term, and identify the terms with bad estimates. In the case, the terms with bad estimates are this and this. Okay. Then we impose this additional condition. Okay. And now with these 2 additional conditions, now the homogeneous system has 7 linear equations and 8 non-decays. Okay. Therefore, it's possible to choose a non-trivial solution bounded independently of m. Then we have 50. And on the other hand, the estimates from below is given in this lemma. Okay, this lemma is obtained directly using estimates of pk here and Minkowski inequality and all the factors sum this. Well, with the sequence pk, we can also obtain an explicit initial data for Stokes equations with memory. because a observation phi t is a data for adjoint problems, and you prove that the observability inequality is not true, then we don't have null controllability. But we can construct a initial data for the Stokes equation directly. Okay. Well, then with the sequence pk, we can also obtain an explicit initial data for Stokes equation that cannot be true drive to zero. Okay, the initial data can be defined this way. Okay, this way, and by contradictions, if you admit that there is a control V such that at final time the solution is null, or that is U at time t is null, from the equations we get this identity. Okay, x1 equal to x2, x1 equal to x2, but from star we get these estimates. Okay, and again take n large enough, we have a contradiction. Then R is not control. Okay, there is not control. Here we have that the same result of the lake null controllability for Stokes equation with memory can be obtained when considering distributed contours. Okay, to obtain these results, we used arguments of extensions and contradictions. A remake is that this result is still wrote if you replace the memory term by this term. Okay, here we have U instead Laplacian U. Okay, additional results. The first is that the for two-dimensional case, the proof is similar. And the main difference is that the pk, the aid function pk in this case, depends on J1, where J1 is the first order Bayesian function and of the first cut. Okay, and qk, the pressure qk, still is null. In the three-dimensional case, the aid functions depends functions same. Okay. Next, other results is that we prove that approximate controllability for Stokes equations is true using n-1 scalar controls. Okay, but for three-dimensional case, using on one control, this is not true. Okay, here we have a Poisson equation with memory, where we have addition this linear term in blue, this linear term, and it would be interesting to analyze this system, thinking about the Android system. Okay, but I don't know any controllability results for this equation. It's open. This question. Other questions is it possible to use moving contours for Stokes with memory? This because Chaves, Jose, and Zuazua proved null controllability for a similar system, but for Stokes equations with memory, it's open too. Here we have some reference, and thank you very much.
Thank you, Lucas. Are there any questions or comments?
So if I may, I have
Yes,
one
Sylvain.
question. So Lucas, thank you very much for your talk. I was wondering when I was listening to your proof that it seems to be related to the case where your domain is a ball, right?
Yes.
So how do you prove it when it is not a ball? Do you prove it? No?
We prove in a ball, and the general domain is a consequence.
Is it, sorry?
We prove
Yeah.
in the ball, okay? And the general domain is consequence of this case.
Okay. And so at the end, can you construct a solution which is localized somewhere?
We construct the solutions explicitly. Some are symmetric functions, and we can computations and can find these 8 functions.
No, but maybe I did not understand that precisely. So your construction is explicit,
Yeah.
but it involves eigenvectors of the Stokes operator in the ball, right? Which are not that explicit.
I don't understand.
In your construction, the construction of the counterexample is something which involves the eigenvectors, well, the Bessel functions in 2D and the eigenvectors of the Laplace operator in the ball, right?
Yeah.
So this is not very explicit, in fact.
Is this? Yeah.
Yes, but then you sum them, right?
Sorry?
You do a summation of these guys, right?
Yeah. In the ball, we find the radial functions and computations, and you find these 8 functions.
Yes, and then the solution you consider for the counterexample, which one is it?
Oh,
In your construction, this is the sum of phi k with some coefficients, right? For the counterexample.
the coefficients. Oh, no, sorry.
Okay, how do you show that the observability is not satisfied?
Sure. No, I don't understand.
Okay, here.
Yeah, sorry.
Okay, next slide, please. Okay, my point is that you will do a linear combination of these eigenfunctions, right?
This linear combination?
Yes.
Okay.
So at the end, your counterexample is not very explicit.
The explicit, yeah, because you question the coefficient decay, yes?
I'm just saying that it is not very explicit. And okay, maybe it's simply a comment, but I remember that there is a work by Debayan Maiti on the controllability of the compressible Navier-Stokes equation, where he was able to construct explicitly counterexamples by looking at the symbols of the system of a PDE.
Yeah.
And it is somehow very explicit construction. So I was wondering if it is something that could be done in your case.
explicit, but in the size of the pk is explicit, and bk, okay, dependent of the solution of a homogeneous system. Okay, you can construct, but the coefficient bk depends of the solutions of a system, homogeneous systems.
Okay, thank you for your answer.
Any other questions? Somebody? Morgan Mohansei says, how robust is the lack of controllability with respect to the regularity of the considered initial conditions? Can controllability hold if one considers more regular initial conditions? That's Morgan. So he cannot use the microphone.
Here we consider U0 in 8 and V in the control in L2. Then we have the solutions in the transposition sense.
Yes, but he wants to know if the bad result, let's say the non-controllability result is robust with respect to the regularity. That means if you put more regular initial conditions, you have the same result or not, or is related with the regularity of the initial conditions or not, the lack of controllability?
And I don't know.
You don't know, okay. So, any other question or comment?
Okay, I have a question. At the same time as a comment, is that what would be interesting here to know if the nonlinearity of the original problem, in which transfer the turn on coupling to a nonlinear hyperbolic system, if the nonlinearity changes the result. I mean, is it possible to get a local controllability result for the original nonlinear problem? Also, for this linearized version, you don't have null controllability.
I don't
have you looked at this? Do you understand?
Not lesson. Repeat, please.
Yes, I was saying that for the original nonlinear problem, you have more terms. You have nonlinear terms in the equations. And in fact, you have a system, not only a motion equation. You have the motion equation coupled to a hyperbolic system for the other unknown, which is tau. So it's the fact, the presence of nonlinear terms is able to change the result. I mean, the null. Have you looked at the effect of nonlinearity with respect to controllability in this system?
Well, for nonlinear systems, I think that we solve first the systems because it's the first approximation. But I don't know. in the case if Z is 0, we have the Stokes equation with memo. But I don't know Z is different to 0. I don't know. I don't know.
Okay.
Well, I think
Thank
that
you.
we should finish here. Thank you very much, Lucas, again, and Jorge, and see you next week.